In this recording, we're going to talk about 7.3 Radian measure. Now, we have grown up just learning about degrees, which has been fine, but they're really, if you think about it, pretty arbitrary. Why did we decide to call a full circle 360 degrees? Somebody just made that up. Now, it gets to be a bit of a problem with us when, as we are doing right now, where we want to talk about the trig functions, sine, cosine, and theta, as being functions. And so we want to be able to mix them in with all the other functions you've studied in your Algebra 1, Algebra 2, and Geometry days. You know, when you talk about a parabola being, y equals x squared plus 2x minus 3, or a straight line, y equals mx plus b, or an exponential, we want to put sines and cosines and tangents and be able to mix them in. The problem is, the other functions that we have take inputs that are real numbers and give outputs that are real numbers. So it's real numbers in, real numbers out. They are unitless numbers. We may choose to give them units based on whether we're going to try to use them to model some situation. We might be talking about the height of an object t seconds after we've thrown it, but the functions themselves are perfectly okay with just plain old numbers. But then what we're doing with our trig functions is something totally different. We're talking about a sine or a cosine or a tangent, and we are talking about inputting something in degrees, and then what we get for an output is just an ordinary plain old number. And so this is just inconsistent. It doesn't mix well with the other things that we're doing. And so that's our motivation here, to redefine our idea of an angle to not be in degrees any longer, but to define it in terms of something else that we're going to call a radian, that is going to be just a unitless number, just a plain old number, so that we can put numbers into our trig functions and get ordinary numbers out, like our other functions. So let's talk about what we're going to call a wrapping function. So I've drawn here a unit circle, a circle of radius 1, centered at the origin. Now imagine that we're just going to take a real number line, and we're going to draw that real number line so that it is tangent to the circle. It just touches the circle in one point at that point 1, 0. And we're going to put the positives up here, the negatives down there, and 0 is going to be that point right at 1, 0. Now this is a real number line, so it's got all of the real numbers there. So in those positives are included things like 1, 2, 3, 4, but also things like pi or e or the square root of 5 or anything else. And likewise for the negatives. Now we're going to imagine that that number line is very flexible, and we're going to take it and we are going to wrap it around the circle, taking just the positive parts first, and we're going to wrap it around here over and over and over and over again forever, so that every real number has a place on this unit circle. There's a place where it lands. Now every place on the circle is going to have an infinite number of points there. So you're going to get that first point there, but then you're going to catch another one as we wrap around there further times, but that's okay. Then we're going to take the negative part of our number line, and we're going to wrap it around going in this direction, going clockwise, and we're going to wrap it all the way around over and over and over and over again until every real number has a place on that unit circle. Now let's think about this for a moment, about what the implications are. So in one trip around this circle, in one trip going around counterclockwise there, we know that the circumference of a circle is 2 pi r. In our particular case here, we have chosen the radius to be 1. It's a unit circle. So that means one trip around that circle is a distance, a length of 2 pi. We're going to call that 2 pi radians. So that's what we're going to mean by that. Now we're going to talk about an angle then as not this kind of weird idea we've done before where is kind of like the space in between two rays that we call the angle. We're going to think of the angle now as being a distance we travel around that circle. So if we go a length of 1, now let's see, if I travel along here counterclockwise, a length of 1, I'm going to call that 1 radian. So that arc length of 1 that I traveled around here is going to define an angle of 1 radian. Now remember that there's 2 pi radians in a full circle. That means that half of a circle, a semicircle, is going to be 1 pi radians, and that means that an angle that is a quarter of a circle, what we would have called a 90-degree angle before, is going to be half of pi. That's pi over 2. So our angle of length 1, if we go this arc length of 1, since pi is roughly 3, then an angle of 1 radian is very roughly 1/3 of that way of that semicircle, which would be really roughly about 60 degrees. A little bit less. It's a little closer to about 57 degrees. Okay? Now, so then what we can do is we can pick any number we like, and we can travel around that circle, that length, and where we end up is the angle that we're talking about. So if I was going to talk about, say, maybe an angle that is a -2 radians. Now I'm emphasizing them by naming them radians, but in fact these are unitless. So in general, what we're going to do is just call this -2. So it becomes even more imperative that if you're talking about an angle in degrees, that you're going to use that little degree bubble symbol. Otherwise, if you don't, it's going to be understood to be radians. So a -2 means I'm going to travel in a negative direction. I'm going to go clockwise. So there's about 1, there's about 2, somewhere in here, and this angle is going to be that angle theta that is a -2 radians. Okay, now let me make a point too. It's really nice to conceptualize when you think of the radius as being 1, because then exactly that length that you travel around the circle is your angle in radians. But it's not restricted to that. If we start with a circle of radius 1, centered at the origin, if we take a radius of a circle of a different radius, so this has radius r, and we're going to say this has radius 1, then if we just extend this angle, remember that this is our arc length, or angle, of 1 radian, roughly 57 degrees. That's the same angle that is intercepted by an arc length of 1 radius. So whatever the radius of that blue circle is, if we travel that length, that is going to be 1 radian, right? Because remember, our circumference is 2 pi r. So if we travel 1 radius length, there are going to be 2 pi of those radius lengths in one trip around the circle. That is 2 pi, roughly 6.28 radians, makes one circle, one circumference of a circle. So it's not tied necessarily to the radius of the circle, except that a length of 1 radian, an angle of 1 radian, will be an arc length of 1 radius. Okay, let's slide down a little bit and see if we can get an idea of what these are. So here is our circle, and we want to see what will an angle of 1 radian be. So remember, thinking that there are 2 pi radians in one circle. I'll say 1 revolution of a circle. So a full circle is going to be 2 pi radians. That means pi radians will be a semicircle, and pi is just a little more than 3.14. So traveling 1 radian is almost 1/3 of the way around the circle. So there is an angle of 1 radian. An angle of 2 radians would go then a length of 2. There's 1. There's going to be 2 somewhere over here. Here is an angle of 2 radians. An angle of negative 3 radians will go clockwise, so in the negative direction. And remember, pi is 3.14, so an angle of 3 radians is going to be just short of halfway around that circle. There's our angle of 3. And we'll still think of these as being, angles like we have before. It's just that the way we get there is going to be by traveling an arc length. Okay? So let's go further and talk a little bit about conversions. So what we know is that 2 pi radians is the same as 360 degrees. So if you are a chemistry student or some kind of science student, you know that if we divide by 360 degrees, say I divided both sides by 360, we would get what science people refer to as a unit factor. That is, if you multiply something by 2 pi over 360, or let's go ahead and reduce that to pi over 180 degrees, that's like multiplying it by 1. In a similar fashion, we could have divided by 2 pi and gotten that 360 over 2 pi, or 180 degrees over pi, is also a unit factor. So we will use these when we need to convert from degrees to radians or from radians to degrees. So, for example, if we have something like, say, 225 degrees and we want to convert that to radians, then we look at our choice of unit factors, and these are our choices, and we recognize that we want to get rid of the degrees, so we want to get rid of that degree bubble. So we're going to multiply by the unit factor that has degrees in the denominator, so we can imagine that we are going to cancel our unit of degrees, and what we will get is going to be our unitless measure, our angle in radians. So we have that 225 over 180. Of course, we can reduce that. Let's see, we can certainly go by 5s. I think this will go all the way down to, I think it's going to go to 5/4, I believe. That'll go all the way down to 5/4, and we still have the pi. In a similar fashion, if we had something that was, say, 5 pi over 6 radians, and we want to convert that to degrees, then we look for our unit factor that will give us degrees, and we'll get rid of our radians. And don't equate pi's with radians. Just the really nice angles have multiples of pi in them, but not everything. So we can cancel those. We can say 6 goes into there 30 times. And so when we multiply, we're going to get 150 degrees. So a 5 pi over 6 radian angle is equivalent to a 150 degree angle. So we need to be able to convert from degrees to radians, radians to degrees. But we don't want to live in that world where every time we get an angle in radians, we're going to try to convert it to degrees so that we understand what it means. That's going to lead to a very frustrating and discouraging existence. So instead, we want to learn to think in terms of radians. And so I'll tell you what I mean by that, so that we don't have to fully convert all the time, but we get a feel for what do we mean by a pi over 3 angle or a pi over 4 angle or so on. So remembering that, going around in the positive direction, a semicircle is going to be an angle of pi. All the way around the circle is going to be an angle of 2 pi. If we then divide those into halves, so if we think, I like to think of this angle here, this semicircle, this angle right here, as being 1 whole pi. So, if you will, this straight angle or 180-degree angle is an angle of 1 pi. Then if we divide that in 2, then we get this as an angle of pi over 2. This is an angle of 2 pi over 2 or 1 pi. This is going to be an angle of 3 pi over 2. And this will be an angle of 4 pi over 2 or 2 pi. Similarly, you can come around, whoops, my hand is touching this in a sensitive place. So remember, this is also, dang it. So this is also an angle of negative pi over 2. So we can also then further divide our pi over 2 into half of the half. So an angle here is going to be pi over 4, which we may recognize as a 45-degree angle. And then this would be a 2 pi over 4, which is the pi over 2. This is going to be a 3/4 pi, which we will call 3 pi over 4. Here is our 4/4, which is 1 pi. This is going to be 1 1/4 pi, which we will refer to as 5 pi over 4. You can also think of it as 5/4 pi. This is going to be 6/4 or 3 pi over 2. We're going to get 1 3/4 or 7 pi over 4. And then again, 8/4 pi is the same as our 2 pi. We can further subdivide this into thirds. So think of our whole 1 pi, and if we divide this into thirds, then we're going to get this angle right here is pi over 3, 1/3 pi, and that's the same thing as a third of 180 degrees. That's the same as a 60-degree angle. This is 2 pi over 3, so this is going to be our 2 pi over 3, which is 120, and then here is going to be our 3/3 pi, and then we will get our 1 1/3, which we'll call 4/3 or 4 pi over 3, and down here we're going to get our 1 2/3 or 5/3 or 5 pi over 3, and then here's our 6/3 or back to 2 pi. Finally, we can subdivide this into 1/6, whoops, doggone it, didn't want to erase that. I'm going to go 1/6 of a pi here, which is pi over 6, and remember 1/6 of 180 degrees is 30 degrees. This is going to be our 2/6, which is 1/3, 3/6, which is 1/2, 4/6, which is 2/3, and then here's going to be our 5/6 or 5 pi over 6. This is going to be 6/6. We're going to get 1 1/6 or 7/6 or 7 pi over 6. There's 8/6 or 4 pi over 3, 9/6 or 3 pi over 2, and 10/6 or 5 pi over 3, and here's going to be our 1 5/6 or 11 pi over 6, and finally getting us to 12/6 or 2 pi. Okay, that's the way I'm going to encourage you to try to think about this. Okay, let's talk about arc length a little bit. Now, arc length in degrees is a little bit awkward, but works out really slick in radians. So if we had a circle of radius 24 feet and an angle of 30 degrees, so you can imagine, we've got this circle, we're looking at a 30-degree angle, and we're trying to figure out what is that arc length. And I don't know why, but they always call that S. So arc length is referred to as S. Well, we could think of what fraction of the whole circle is that 30-degree angle. It's 30 degrees out of the 360 degrees. So we could take that fraction of the circle times the whole circumference, which is 2 pi r. So the 30 over 360 reduces to 1/12. Since our radius is 24, we could call that 48 pi feet, and we could cancel because 12 goes into 48 evenly, and we would say it's 4 pi feet would be that arc length that 30 degree angle subtends or spans in a circle of radius 24. So let's consider how we would do this now in terms of radians. Now here's our definition, which is kind of cool. An angle in radians is the arc length divided by the radius. So if the radius is 1, then the angle in radians is just the arc length. And if not, then you divide by the r. So you can see that if we take that angle in radians and multiply it by r, we get the arc length. That's pretty slick. So that means if we already know our angle in radians is 2 pi over 3, and if we use that same radius of 24 feet, then it's pretty pain-free to get that the arc length is going to be 16 pi feet. Kind of cool? Let's do a couple more examples. So here's one where, again, our angle's in degrees. So we're going to take that 150 over 360, make that fraction, times 2 pi r. And since the radius is 6, that's going to be 12 pi. We can reduce this. Let's see, I think 30 goes into there 5 times and into there 6 times. We can then cancel the 6 with the 12. And so what we're going to end up with at the end of the day is 10 pi in centimeters, I guess, is going to be our arc length. Okay, let's do it in radians. We're going to take our angle in radians, 3 pi over 4, times our arc length, our radius rather, 6, and we can reduce a little bit. 2 goes into each of those, and so we will get a 9 over 2 pi, or if you like, I guess you could call it 4.5 pi, and that's going to be our arc length in centimeters. Okay, I think we're ready for the next panel. Sine, whoops, yikes, come back here, times the sine of our angle, still in radians. And where did I go? Where did I go? Oh, I hit the... So we're going to revisit now what we started talking about earlier, how we need to know the values of these, of sine and cosine of these known values, 0, 30, 45, 60, 90 in quadrant 1, and then we're going to extend that to any multiple of that in a positive or negative direction. Well, now we want to be able to do that not only in degrees, but also do it in radians. So let's recall what we get in degrees for a moment. Remember, sine starts small, and so it's going to start, sine of 0 is 0, and then it's going to gradually get bigger. So it's going to go 1/2, square root of 2 over 2, square root of 3 over 2, and 1 is the biggest it can be. Cosine starts big and gradually works its way smaller. So it's going to go square root of 3 over 2, square root of 2 over 2, 1/2 to 0. Now, what we want to do also is to be able to recognize how, just as we can see these angles go from the smallest one we're going to need to know from memory is 0, then 30 degrees, then 45 degrees, and then 60 degrees, and the biggest one in quadrant 1, it's not really truly a part of quadrant 1, it's the boundary, would be 90 degrees. Now we can do this same thing in radians. So remember, this is 0. This is going to be 1/6 of a circle, 1/6 of a pi, 1/6 of that semicircle. This is 1/4. This is 1/3, and this is 1/2. Notice as the denominators go from big to small, the values of the fractions go from small to big. So in radians, we go 0, pi over 6, pi over 4, pi over 3, pi over 2. So if we ask you, for example, what is the cosine of pi over 3 in your mind's eye, and I'll give you hand gestures to go with this, we would say, let's see, pi over 3, we go 0, pi over 6, pi over 4, pi over 3. So it's 1, 2, 3, 4 clicks. Cosine starts big, so it's going to go 1, square root of 3 over 2, square root of 2 over 2, 1/2. So the cosine of pi over 3 is 1/2. And that's the reasoning we're going to use there. All right, let's see what else we've got here. So a couple challenging problems. In this diagram, we have two diagrams. So we're going to do two of these examples. We are going to find out what is the radius r, what is theta, both in degrees and in radians, and what is the arc length s, and what are the coordinates of the point P. Now, we're going to need our calculator for some of this, but let's see what we know. Well, if the point, this time we're given the point, there's our 7.3, the coordinates. So that means if we imagine dropping this perpendicular down there, then we know that this is going to be 7, and this vertical distance there is going to be 4. The radius, we can see, is going to be then Pythagorean. Okay, I'm back. I hit the wrong thing with my hand. So our radius, I got to bring my pen back up here. So our radius is going to be the square root of 7 squared plus 4 squared. That's going to be 49 plus 16 is going to be the square root of 65. So our r is the square root of 65. So that's one thing we wanted to know. Now we need to know the angle in degrees and also in radians. So let's do it in degrees. We're going to need our calculator. We can see that the opposite side is 4 and the adjacent side is 7. So we can say the theta is going to be the inverse tangent of 4 divided by 7. And I think if you do that, I did my calculators in radians, so I'm going to give you this one in radians first. That's going to be rounded to 3 decimal places, is going to be 0.519. 0.519. Now to find theta in degrees, we can do one of two things. We can change the mode on our calculator to degree mode and go inverse tangent of 4/7, or we could take our, not our rounded value, but that exact value on our screen and multiply that by 180, I meant to write, 180 degrees over pi radians. So I'm going to take the answer on my screen and go times 180 divided by pi, and I'm getting 27.745. 27.745 degrees. So there's our angle in both degrees and radians. Now the arc length, remember our S, I'm going to change colors there, S is going to be, I can take that angle in radians times the radius. So I think that's going to be the most efficient way. Our radius, we said, was at square root of 65, and I'm going to multiply it. I'm going to write 0.519, but I'm going to up arrow, I'm going to scroll up and grab all of that when I do the actual multiplication. So I'm going to go on my calculator, second x squared square root of 65. I'm going to right arrow out of that, times, then I'm going to scroll up and get that 0.51914611142 and hit enter. And then rounded to 3 decimal places is going to be 4.185. 4.185. So I think we've gotten everything there. Let's take a look at the second one where we have a little different information here. So let's see. We have the angle in radians is 1.3. We can tell it's radians because there is no degree bubble written there. And let's see, we know the point over here is 12.0, so I guess that tells us right off the bat that R must be 12. Now we've got theta, so we can find theta in degrees easily enough. So I'm going to, on my calculator, I'm going to take the 1.3 and I'm going to multiply that by 180 degrees and divide by pi. And so I'm going to take that 1.3 times 180 divided by, I'm going to try that again, 1.3 times 180 divided by pi, and that's going to be, I'm getting 74.485, 74.485 degrees. So we've got our angle in both radians and degrees. We've got the radius. I think arc length is going to be pretty easy to find here, since arc length is our angle in radians times the radius. And we have that is 1.3 is our angle in radians. And we said the radius was 12. So I'm going to go 12 times 1.3, and that looks like 15.6. Now we got the x coordinate of that. Nope, we got to find the x and y coordinate of point P. Now this is a little more challenging, so this may be the first time, I don't know if we've done this. I think maybe we have. So if we know our angle in radians, then I can call this x and that y. That's the x and y coordinates of our point that we're trying to find here. Now we know that the cosine of theta is the adjacent x over the radius, which we have is that 15.6. So we can say that x is going to be 15.6 times the cosine of theta, which we know in radians is 1.3. So I'm going to do this on my calculator. Check your mode, make sure you're in radian mode. I am. So I'm going to go 15.6 cosine of 1.3. Whoops, I didn't do that right. 1.3. And that I'm getting is 4.173. 4.173. In a similar fashion, we know sine theta is y over r, and so we're going to get y is the radius, 15.6 times. There I am. Holy smokes. This is what happens when you're left-handed and you try to write on these things. So we're going to go sine of 1.3. So this is going to be then 15.6 times the sine of 1.3, and I'm getting 15.032. 15.032. All right, very good.